Hello class. The tentative schedule of our course is to start with Chapter 4, Fundamentals of Statistics, followed by control charts for variables. Next, we're going to cover fundamentals of probability, followed by control charts for attributes. And our semester will conclude with reliability. Excel provides us a lot of useful formulas and tools to help us compute these statistics and draw diagrams. So if you are totally uncomfortable with Excel, you should reconsider taking this course, or you need to get some help on basic operations of Excel. Here is the outline for Chapter 4, and today we are going to cover the first two sections, Introduction and Frequency Distribution. After today's lecture, you should know the differences between a variable and an attribute. You should be able to perform mathematical calculations to the correct number of significant figures. You also need to understand categorical, ungrouped, and grouped frequency distributions. So, what is statistics? There are two generally accepted meanings. The first one is statistics is a collection of quantitative data pertaining to a subject or group. Examples are blood pressure statistics, football game statistics. So you can view the statistics as a function of your data points. The second one is a broader definition. It says statistics is the science that deals with the collection, tabulation, analysis, interpretation, and presentation of quantitative data. The use of statistics in quality deals with the second and broader meaning. There are two phases of statistics. The descriptive statistics can only be used to describe the group that is being studied. That is, the results cannot be generalized to any larger group. Frequency distributions, central tendency like mean, and graphics like pie charts and bar charts that describe the data are all examples of descriptive statistics. Inferential statistics is concerned with making predictions or inferences about a population from observations and analysis of a sample. That is, we can take the results of an analysis using a sample and can generalize it to the larger population that the sample represents. In this case, the language of probability is used to show how well the sample represents the population. There are two types of data. The first type is called attribute. So attribute data can be classified as either conforming or not conforming to specifications. It has a binary nature, so each entity can be labeled as either 1 or 0. For example, we can record if a patient is having or not having a fever, if each part has met or not met the specification, and we can record if each student is late or not late for the class. The second type of data is called variable. So variable data is measurable, such as weight measured in pounds. Continuous variable is capable of any degree of subdivision, such as weight, length, and time. And variables that exhibit gaps are called discrete variable. So, for example, the body temperature of each patient, we can measure the dimension of each part, and we can record the arrival time of each student to our classroom. In working with numerical data, significant figures are very important. When you measure something, there's always a room for a little bit of error. For example, what is your height? Is it 5 feet 6 inch or 5 feet 6.1 inch? So significant figures are used to indicate the amount of variation which is allowed in a number. Counted number is assumed to have an infinite number of significant figures. So if I claim that we have 28 students in our class, then you can put unlimited number of zeros after the decimal point. The definition of significant figures is that digits exclusive of any leading zeros needed to locate the decimal point. So in a simple word, you start with the first non-zero figure, and every figure afterwards are counted as significant. For example, 0.0369. The first non-zero figure is 3, so 3, 6, 9 are 3 significant digits. And how about the second number? 36.900. The first non-zero figure is 3. So 3, 6, 9, 0, 0 are 5 significant digits. When we are using scientific notation, we should only count the significant figures in the digit term, not in the exponential term. When you're multiplying or dividing numbers, then the number of significant figures of the result should be the same as the number with the least number of significant digits. For example, 6.59 times 2.3. 6.59 has 3 significant figures. 2.3 has 2 significant figures. You took the minimum of these two, which is 2, and therefore the result should have 2 significant figures, and we record it as 15 here. If 24 is not a counting number, then 24 has 2 significant figures. You take the minimum of these two numbers, and then the result should have 2 significant digits. Now, if 24 is a counting number, then we consider that this 24 has infinite number of significant digits, and 32.64 has 4 significant figures. So now you take the minimum, which is 4, and the result should have 4 significant digits. When you are adding or subtracting the numbers, then the number of significant figures of the result should be no larger than the fewest significant figures after the decimal point. We have similar examples as the previous slide. The only difference is that we are counting the significant figures after the decimal point. Measuring instruments may not give a true reading because of problems due to accuracy and precision. So the precision of a measurement is determined by how reproducible the measurement value is. For example, there is a sample that measured by one student is 24.58 grams, and then another student measures 5 times, and then he gets this set of measures, and we can see that the original measurement is not very precise because it cannot be reproduced by the second student. The accuracy of a measurement is determined by how close a measured value is to its true value. So for example, if we know the true value of a sample, the true weight of a sample is 3.182 grams, and then we weight it 5 times with these results, then the most accurate measurement should be 3.180 grams, because this is closest to the true value of the sample. So here is a figure that demonstrates precision and accuracy. The cross stands for the true value. So if all the measurements are close to the true value, then they are accurate. If the measurements are close to each other, then they are precise, but they may be far from the true value. If the measurements are close to each other and also close to the true value, then the measurement is both accurate and precise. We can describe a set of data by frequency distribution, measures of central tendency, and measures of dispersion. So we first start with frequency distribution. There are three types of frequency distribution: categorical, ungrouped, and grouped. Here is the set of data that we have collected last class. I asked you to input your month of birthday, and we have a total of 22 entries. Categorical frequency distributions are suitable for data that can be placed into specific categories, such as nominal or ordinal level data. For example, political affiliations, blood types, etc. So here is the birthday month frequency distribution of our class. The first column is called class, which is just the same as categories. So we define like 12 categories from January to December, the 12 months. And the second column is called frequency. So we count the number of students in our class who were born in each month. Therefore, you can treat frequency as a fancy word of count, and frequency distribution is just a fancy word of table. Another example is students' letter grades. So we classified the students' grades into A, B, C, D, and F, and we count the number of students in each category. Ungrouped frequency distributions can be used for data that can be enumerated and when the range of values in the dataset is not large. So two keywords, enumerated and limited range. The examples include numbers of girls in a 4-child family, numbers of daily billing hours in a company, etc. On the left-hand side, we show the data for 52 days, recording the number of daily billing hours in a company. And on the right-hand side, that's the frequency distribution. So the classes in the ungrouped frequency distribution must be enumerations, must be numbers, 0, 1, 2, 3, 4, up to 5 errors. And the second column records the frequency of each class. Another example is the number of girls in a 4-child family in Cape. So the number of girls in a 4-child family can only take the value of 0, 1, 2, 3, and 4. And then we can record how many families are in each class. Grouped frequency distributions can be used when the range of values in the dataset is very large. The data must be grouped into classes that are more than one unit in width. So we take an example as the life of both batteries in hours. So we need to define the class boundaries. These boundaries should be continuous so that they can be linked head to tail to cover the whole range. So, for example, like the batteries that can last between 23.5 months to 27.5 months are 4. Therefore, it records the frequency of the both batteries within each class boundaries. Another example is students' numerical grades. So we cannot like have 100 categories or 100 classes. Therefore, we define the class boundaries from 90 to 100, from 80 to 89, and until 0 to 50, and then we record the frequency, aka the number of students, within each class boundaries. Please read the section of frequency distribution in Chapter 4. We are going to cover the histogram next class.